that filtration doesn't vary with fluctuations in blood pressure. That net filtration pressure remains relatively stable. And this is called the myogenic mechanism. Okay. I'm drawing here the renal pyramid. Here's the cortex. So here's your PCT, here's your weaker family. Here's your DCT, and look, these cells right here would make up your macula densa. Okay. And we said that macula densa cells are osmoreceptors. They sense concentration of the filtrate. Okay. Now, the second mechanism that serves to maintain a steady net filtration pressure and steady GFR, let's go back, that's called the tubulo-glomerular feedback mechanism. It's got a fancy sounding name. It's a redundant mechanism. It backs up the myogenic mechanism. Okay. Purpose is the same. It maintains a steady net filtration pressure, so our glomerular filtration rate doesn't change throughout the day, at least as long as our blood pressure doesn't fall into extreme ranges, way too high or way too low. With the normal fluctuations of blood pressure, our GFR is going to remain stable. Okay? By the way, the body is full of redundant mechanisms. You know, think about what we've learned so far. Baroreceptors. We have baroreceptors in a carotid sinus, but we also have baroreceptors in the aortic arch. It's kind of redundant. Okay? So that if there's failure at one site, there's another site that's still functional. It's a backup mechanism, so to speak. So in the same way, there are redundant mechanisms with these internal controls. Let's say blood pressure begins to fall. Okay? There's a drop in blood pressure. That's not only going to activate a myogenic response, but it's also going to trigger a tubulo-glomerular feedback mechanism. Okay? If blood pressure falls, okay, then flow through the glomerulus and initially filtration might begin to slow down. Okay? If this myogenic mechanism doesn't kick in immediately, then as the blood pressure falls, net filtration pressure is going to fall, and rate of filtrate is going to fall, the glomerular filtration rate. If we have less filtrate being formed here in the capsule, then flow to the renal tubule is going to be more sluggish. Okay? As flow to the renal tubule slows down, it provides more time for reabsorption. Okay. So by the time this filtrate reaches the JJ apparatus, there's a decreased concentration of sodium chloride within the filtrate. It's been reabsorbed to a greater extent because of the sluggish flow. So the concentration of salt reaching the JJ apparatus is decreased. Well, the cells of the macula densa are going to detect that decreased concentration because they're osmoreceptors. Okay. These cells then release nitric oxide to the smooth muscle-like cells that surround the afferent arteriole, to the JG cells. Nitric oxide is going to be a vasodilator. So in the face of decreased sodium concentration as a result of sluggish flow, we're dilating the afferent arteriole to allow more flow into the glomerulus. Okay. Now you might say, well, the problem is blood pressure. Okay. What also happens in the face of decreased sodium concentration at the JG apparatus is that the JG cells release renin. Okay. We've talked about the renin-angiotensin pathway. If the JG cells release renin, we activate the renin-angiotensin pathway, we form angiotensin II, which is going to cause vasoconstriction of the arterial and venous. That's going to help raise blood pressure. We're also going to produce aldosterone, which is going to help us to retain water volume. So in that way, we increase blood pressure. But this mechanism serves to maintain a steady hydrostatic pressure and therefore steady glomerular filtration rate. Okay. Of course, the opposite happens if blood pressure is high. If blood pressure is high, then the flow of filtrate is more brisk. It has less time for reabsorption of sodium. So by the time the filtrate reaches the JG apparatus, the filtrate concentration of sodium is higher. That inhibits release of nitric oxide. And in the face of high blood pressure, without nitric oxide, the afferent arteriole vasoconstricts. Okay? That allows less blood into the glomerulus. Then filtration pressure falls. We form less filtrate. We normalize. Okay? With this tubuloglomerular mechanism, we have to kind of think through it. Okay? But it's a redundant mechanism which basically serves to maintain a steady GFR. This would be a diagram from one of your books that just kind of outlines the process. Okay? So if you have some stimulus like high blood pressure, that would ordinarily cause an elevation in net filtration pressure. Why? Because it raises glomerular hydrostatic pressure. Then as net filtration pressure increases, so does glomerular filtration rate. Okay? With a rapid or a higher net filtration rate, you're going to have more rapid flow of filtrate through the renal tubule, giving less time for reabsorption of salt. So the macula densa cells are going to detect an increased delivery of salt, sodium and chloride and water, okay? Which is going to result in decreased secretion of nitric oxide, and the afferent arterioles constrict. Okay? What that means is that less of that high blood pressure is going to reach the glomerulus, okay? And so that GFR is going to come back down to normal. Again, for this one, you may have to spend a few minutes outside the class and just going through the steps. A lot of anatomy and physiology is just connecting the dots. Okay, so this leads to this, to this, to this, to this, to this. Some of you pick these things up quickly. Some of you it'll take a little bit more time. It's okay. The most important thing is that by the time you're tested on it, that everyone has kind of incorporated the knowledge. Everyone has different rates of learning. It's okay. Some of you will have to go back home and look at this one. So this autoregulation, these intrinsic mechanisms, operate over a normal range of blood pressure. Because during the day our blood pressure fluctuates depending upon activity. Right now, Abby's blood pressure might be 100/70. If her good friend Jordan comes into the class and he gets excited, her blood pressure may climb up to 140/90, right? Yeah, that's what I'm saying. Yeah, thank you for that. And so the blood pressure is going to vary. Well, as long as it's fluctuating within normal range, these intrinsic mechanisms kick in, and our urine output doesn't change. We don't, all of a sudden start peeing a lot or peeing less because of a difference in filtration rate. Now, these intrinsic mechanisms, autoregulation, however, ceases when blood pressure either climbs or drops into extreme ranges. So autoregulation works well between, let's say, a blood pressure, a systolic blood pressure of 80 to 180. Actually, when systolic blood pressure begins to fall below 90, autoregulation begins to cease. If blood pressure climbs too high, we can no longer maintain a steady filtration pressure. That high pressure head gets translated into the glomerulus, and that really high blood pressure can cause damage. So this autoregulation only functions, only works within normal ranges. Okay? Once blood pressure begins to fall too low, what happens? The sympathetic nervous system kicks in. Hypotension, when JJ comes into the ER, okay, hypotensive, that's a physiologic stress to the body. And so that's going to trigger activation of the sympathetic nervous system. It turns out that sympathetic fibers provide innervation to the kidney. And so when we activate the sympathetic nervous system, these sympathetic fibers release norepinephrine. Okay. Remember, postganglionic sympathetic fibers are adrenergic. They release norepinephrine. And norepinephrine is going to bind to adrenergic receptors, okay, on the smooth muscle, for instance, of the afferent arteriole. And that's going to trigger intense vasoconstriction. Okay? So you're going to get vasoconstriction of the afferent arteriole, which is going to allow less blood into the glomerulus, and all of a sudden we're going to have decreased formation of filtrate. Why? As we allow less pressure into the glomerulus, our glomerular hydrostatic pressure is going to fall. And as that falls, net filtration pressure falls. As net filtration pressure falls, GFR falls. Okay? So we can no longer maintain a steady GFR when our blood pressure falls too low. Instead, the sympathetic response kicks in, and we get intense vasoconstriction of the afferent arteriole. What that does is it diverts blood flow away from the kidneys. You see, in times of sympathetic activation, in times of physiologic stress, we're going to divert blood flow to more vital organs. Okay? Like the heart, the brain. Okay? Now, this sympathetic stimulation also directly stimulates the JG cells to secrete renin. And that's going to reinforce the activity of the sympathetic nervous system to raise the blood pressure. But are we going to pee? No, this is a second mechanism that's responsible for us not peeing. The first is that with a sharp drop in blood pressure, we don't have any glomerular hydrostatic pressure. But on top of that, we're doing this. We're causing the afferent arterioles to clamp down, and we're diverting blood flow to other organs. And then we're activating the renin-angiotensin pathway. Let's look at that. You know you're familiar with this. Okay? You know you're going to be tested on this renin-angiotensin pathway throughout your lives. Doesn't matter what you take. If you take, for instance, pharmacology, you'll certainly be tested on it. Okay? If you take pathophysiology, you'll be tested on it. If you take pediatrics, you're going to be tested on it. Okay? If you take genetics, well, you won't be tested on it. But most of the things you take, you'll be tested on it. Okay? So what it says is that if there's a drop in blood pressure, or drop in blood volume, or increased sympathetic stimulation, any of these three things can stimulate activation of the renin-angiotensin pathway. Okay? And one of the mechanisms is through sympathetic activation of adrenergic receptors on the JG cells. One of the mechanisms is through a tubulo-glomerular mechanism. Okay, blood pressure falls too low, it's sensed by the macula densa cells, it triggers release of renin from the JG cells. Okay? But regardless of the mechanism, the kidneys produce renin. Renin acts on angiotensinogen, which is constantly being produced by the liver. It cleaves off a couple of amino acids. It converts this peptide into this one, angiotensin 1, which is a weak vasoconstrictor. Angiotensin 1 circulates through the pulmonary circulation. You know, it's pulmonary arterial endothelial cells that produce ACE. So it's within the pulmonary circulation within the lungs where it comes into contact with ACE, which converts into angiotensin II. Angiotensin II is going to bind to angiotensin II receptors on the adrenal cortex, trigger release of our friend Al. Aldosterone is going to tell the kidneys, hold on to salt, water is going to follow. So our body's going to retain volume, which raises blood pressure. Angiotensin II is going to cause vasoconstriction. It not only causes vasoconstriction of arteries, but also veins. Both of those activities raise blood pressure. Angiotensin II, if you take cardiorespiratory physiology, you learn it does a couple of other things too. It stimulates release of, for instance, ADH, antidiuretic hormone. Okay, it actually does a number of things, but we'll focus on these right now.
Dr.
Yeah.
When you say the liver holds on to the salt, where is that salt necessarily? Like along the loop, or like what causes that?
What it does is it activates pumps. And we're going to go over it.
Okay.
When you increase pump activity, what happens is along certain segments of the renal tubule, sodium gets reabsorbed at an increased rate. And then water tends to want to follow wherever salt goes because it creates an osmotic pressure, osmotic gradient. How'd y'all do with that? Is everybody good? All right, let's take a break now, and we'll pick up again at 5 after. JJ, you know, JJ, one of the things as a teacher, we're trained to recognize students who are being overwhelmed. That's part of our training.
I'm not overwhelmed, I'm just distracted.
Yes, that's what I'm saying, you're overwhelmed.
I'm not the only one distracted, since you want to put me out of there. I will name a few other students.
I
So don't y'all look at me.
don't think we should call people out. That's just fine.
Don't y'all look at me.
I'm not distracted. I made pretty notes. You want to see my pretty
I don't care, Alyssa. Your notes are ugly.
I colored it and everything.
I don't care.
I like your shoes. It's very aesthetic.
I don't like them no more.